Hi everyone, I'm Shimol, this is Mike. We are here from the Google Enterprise Wi-Fi team. We are here today to talk about OpenConfig. What is OpenConfig? How have we used it to solve our problem statements? We'll try to show you how we have taken OpenConfig and applied it to network programmability, how we have simplified our deployment process, and how do we build and operate our enterprise network today. We'll try to, if there is enough time, we'll try to do a quick demo to showcase how this all works. How can you build and operate a multi-vendor network in one uniform way? Some of you who are attending the deep dive, you guys already know some of this, but if not, we'll be doing it again in February WLPC.
All right. So what is OpenConfig? Anybody heard of it? Show of hands, the word. All right, no, there's more hands going up now than a few months ago, so that's good. It's getting out there. All right, vendor neutral data models interacting, oh yeah, blah, blah, blah. What does all that mean? So basically it's a bunch of network engineers from our operators, we call them, that get in a room and decide what we want an API to look like. So we know we want it, we know we want an API, and we know we want it to be a standard API shared by all vendors. So that's what we mean when we say, you know, it's operator driven. It's just network engineers in a room. No lawyers, no copyrights, no vendors. It's informal, it's on GitHub, open source. Everybody's free to, you know, to take a look at it or join the group. We meet weekly. And you know, we come up with what we want these data models to be, and these data models are just a way to define what the schema of the API should be. So by schema, I mean specifically just, you know, transmit power is called transmit power. You know, it's an integer, it's expressed in dBm. A channel is also an integer. You know, an SSID name is a string. That's really it. At the end of the day, it's pretty simple. And it's just a few data models. GNMI is the transport. So to sort of draw an analogy to legacy terms, GNMI would be like akin to SSH, right? It's the way that the protocol used behind the scenes to actually serialize and deserialize the data, whereas the Yang data models is the schema, just what the data will look like. And GNOI is what's left. It's for operational commands like ping, traceroute, stuff like that. We'll get into that a little bit more later. All right, so the point of this slide is not to like, hey, look, big companies, big names, you know, you guys should like it too. Like, who cares about that? It's actually more to highlight who's not on this slide. So who's not a participant in the working group, who doesn't have say in what the API should look like. And if you haven't noticed, that's vendors. So they are not, you know, participating in OpenConfig. This is sort of flipping the table around. This is operator driven. It's not driven by vendors. We don't expect vendors to get in a room and agree on anything. So this is just network engineers that derive these models and then sort of say, hey, if you want us to buy your stuff, then please adhere to this schema. It's on GitHub. Have a nice day. Come back to me when it's done. All right, so why did we approach this topic, or, you know, why did we sort of go down this path? It was, gosh, what, 2.5 years, maybe 3 years ago? So the problems that it solves, we know we needed telemetry, specifically radio data. And by radio data, I mean the standard stuff we're all used to monitoring that we've been hearing about for days. It's the channel utilization, it's the retries, the stuff that you need to operate the network. We needed radio data and we needed it fast. What do I mean by fast? The old paradigm of screen scraping or using SNMP wasn't fast enough. You don't have to go farther than the vendor's documentation to see that it's, you know, the recommended polling interval of a controller is about 15 minutes. That's pretty much useless. Once you roll up data at a 15-minute interval, most of it becomes normalized. As we know, data is bursty, and telemetry at that sort of aggregate level doesn't solve our problems. we wanted to move away from translation layers. What I mean by that is it's like, so we wanted a uniform tool chain, one tool chain to sort of deploy the network, one tool chain to monitor the network. And you could say, well, you could build that and then write sort of at the last minute before you do your gets and your sets to the vendor's equipment, just translate to their specific version of an API or their specific, SNMP MIB. We did try that. It was difficult for obvious reasons. It was like having to write tools per vendor, and also it broke a lot. MIBs, even APIs, even the new world APIs, they change with vendor versions of code or versions of software that they're running. So automation was actually way more dangerous, something we learned along the way. Automation, more dangerous than humans typing at a CLI, because when that API changes, you're expecting a deployment or your monitoring to not involve somebody running a show command or not involves a build room where somebody's typing commands at a CLI. So if you type a command at a CLI and it doesn't work, you're a human. You hit question mark or go to the, trying to figure out what the right command is. But in automation, that's not true, right? The whole thing kind of falls over when a vendor changes that interaction. So translation layers sucked. And we needed APIs for everything. That's an obvious one. It's sort of the shift in the industry is towards APIs. You'll see some of the new vendors coming out they're not even offering SNMP. They're not running SNMPD on their infrastructure. So, all right. So how does it solve them? On the radio data side, it's about streaming telemetry. I know that sort of OpenConfig has the name config in it, but it is just as much about telemetry as it is config. So streaming telemetry is directly aimed at solving the probing problem. So yeah, SNMP sucks for many reasons, and that's well documented. But even if you're using an API, if you're doing gets, constantly you're polling a system. You're rebuilding that channel to the system, and you're introducing all that overhead every time you do a get. So streaming telemetry is sort of a subscribe. It's referred to as pub sub, publisher subscriber model. You basically send one message to the system saying, I want to subscribe to channel utilization at an interval of, 5 seconds. And that channel stays open, and then every 5 seconds, the system just automatically sends you the channel utilization at that point. So that's a lot less overhead on the system. So streaming telemetry gives us that, it's going after that we need radio data and we need it fast problem. The translation layers, I think I already spoke on that. It's one schema. It's one common set of data models. There's the link, and obviously it's all API driven. It's this whole sort of OpenConfig thing is about an API. So here's the path we took, trying to bring programmatic access or trying to monitor the network and deploy the network in a common way. We had the SNMP stuff, proprietary MIBs. Then we moved on to proprietary APIs, and we had recipes and Ansible and modules, and we even were doing screen scraping for the stuff that wasn't available via an API, having scripts that log in, do show commands, automatically try to structure that data. And that was really difficult because of like I said, you're dealing with unstructured data by nature, so trying to massage that was difficult. And the proprietary API situation is what I already spoke about. When that changes, the whole thing would fall over. So the 2019 is sort of we've been in production with our OpenConfig vendors for about a year, and that's sort of going forward. That's the only way we're doing it. So a little before and after here. I'm going to try and talk fast because I do want to get to the demo. So before we had controllers everywhere. We realized that not to be like a controller versus controllerless argument, because we are agnostic from an OpenConfig point of view. Centralized data plane, distributed data plane, we don't care. We're just talking about the format of the JSON blob that we're sending at you. So, use controllers if you want. We just realized that controllers or centralizing that data plane, the only reason we were really doing that is because of a management plane problem. It made it easy to configure 2,000 APs if I was a human typing at a CLI, when all of those things were configured from one device. But once we approached the automation thing, and it was just machines configuring machines, we didn't care about whether the machine was talking to one endpoint or all 2,000 of those endpoints. We're talking about milliseconds from beginning to end for the configuration pushes and the getting. So needing the controllers everywhere, needing that centralized data plane, that kind of went away when we solved the management plane problem. So config management was CLI access for everybody. You know, we sort of had to train our staff on individual CLIs from the different vendors. That was problematic. And obviously, you know, when a human's doing humans are great at certain things and they suck at others, being repetitive and making sure you don't fat finger something and doing it right and having all of your golden configuration templates and, hey, please follow this document, like it was tough. Mistakes happened. There were actually a large portion of our outages were due to human mistakes. It's a highly distributed network. We're talking about thousands of controllers globally. And then the granularity part, I think I already spoke about that. All right, so post, obviously controllers are where needed only, and controller is sort of a loaded term. We use some vendors that have cloud controllers. Basically, we just call them AP managers. So we've got the whole gamut of those, but we only deploy them where necessary now. Config management, I think I already spoke to that, standard API. No humans. So Shimol is going to touch on that a little bit more, but yeah, we do not have any humans doing configuration or telemetry getting. It is completely automated. So we just sort of removed humans from the deploy pipeline. We killed the build room, all of that stuff. It's literally just a script now. And then the granular telemetry, again, fast pub sub.
Cool. Thanks, Mike. So as we started on this journey, we had to lay down some core principles for us to abide by as we made progress. So something which Mike touched upon, right? We wanted to automate the entire build process. We wanted to automate as much as we could from the operate process in one uniform way. The goal for doing that was, in addition to humans being error prone, it also actually takes a lot of time if humans were to do all this. To be able to grow in a sustainable fashion, we can't grow our network at the same rate as growing our network engineering staff. It's just not tenable. So with that at the core, we laid down some principles. And the principles were quite simple. No humans should have to interact directly with any network devices, whether it's through the CLI or through any other ways. The human is only supposed to drive the automation. Everything downstream should be handled by the automation, right? So the principle is machines configure machines. The humans look after the automation which orchestrates the machines. Network admins, right? Wi-Fi engineers still control where access points get placed. They still control a couple of important parameters like what's the channel width, what is going to be the TX power. But those are the only things they do, and they do it on a graphical heat map, which we'll show in our demo. The configuration generation, the configuration push, the compliance with standards, updating intent, making sure that things are operating, the intent versus the actual state, all of that is done through machines. As we talk multi-vendor and as we talked automating things, typically multi-vendor means multiple troubles. So for the operations staff, this would only work if things are transparent to them. So one of the goals we set up for themselves is our operations staff should be able to operate the multi-vendor Wi-Fi network using one single UI. It should look exactly the same, does not matter what vendor is being used. It should expose all the necessary KPIs to the operations staff. The only time the operations staff should care about what vendor is being used at the site is when they need to do an RMA. And at that point in time, they just need to know that it's vendor X with model Y. So that's pretty much the only information which is vendor proprietary, which we expose in the UI. And we'll show you the UI when we do the demo. So with that, this is the current deployment pipeline which we use. Start from the bottom left-hand side, Heatmap. So that is a manual process. We'll show you the Heatmap for us. It was a simple Google slide. just because it gave us an API. It could be any of the tools which are commercially supported, provided they have an API. The heat map is where we place access points with XY coordinates. We put down the transmit power, channel width, the name of the access point, and so on. All of that is ingested by Wi-Fi front end. It's a configuration tool which a few of us in the team wrote. Again, the team is just a few network engineers with no automation experience. Over the last 18 to 24 months, people have tried to pick up Python the best they can, and this is the outcome of that. It's not fancy. We are going to try to work on open sourcing that, so hopefully by the time we come back in February at WLPC, this should be available, so if folks want to download it and try it out, you can do it. Wi-Fi front end goes and generates the actual configuration. In the back end, it goes and interacts with the various systems it needs to, whether it's the IP address management system, our LVC scanning app, which we give to our installers to scan the MAC address associated to the name of an access point, which gets read by Wi-Fi front end and is used to generate the subsequent JSON file, which Mike referred to and will show in the demo. This JSON file, this OpenConfig JSON file goes into a revision control system. We have our own, but in our demo, we'll show you that it can go to GitHub or any revision control system of choice. Any config changes made get archived over there. It's human readable. So if somebody really wants to see what's the configuration which is running live, they essentially look at that. Beyond that, it gets pushed to the end network device, whether it's based on the architecture, it could be that some vendors let you push config directly to the access point. The GNMI target is the access point. Some vendors want you to push that to their actual cloud AP manager or controller. So depending on that, that's where the config gets pushed. Downstream from the config push, we have our telemetry getter, and I think the next slide goes a little bit more into that, which uses GNMI to extract the state information for every single config element which was configured, and we use that to do some troubleshooting. So this is the operation slide. So start over here. Use in OpenConfig, there is a concept of getting telemetry ad hoc. So that's like when you want to do triggered telemetry gets. So you do a GNMI get. We do it every 30 seconds. You could do it sooner, but that's good enough for us. Much better than what we could do with SNMP. There is also the concept of streaming telemetry, wherein there are certain things which we want every second or 3 seconds. Or for a granular troubleshooting scenario, we want to go down more. So for those, we rely on streaming telemetry. We also use it for error logging conditions. So we don't want to do periodic gets for everything. We only want the device to tell us, should there be a change. So that becomes easy on our TSDB to only ask for information or only be told about information when there is a change. So all of that goes into a database. The database is then used by the various backend systems. As everything, we visualize it for our operations staff, so they have the simple UI to look at. We also feed it into our alert management system, which is essentially has a bunch of rules saying, hey, if channel utilization is high for X number of minutes, go tell somebody. Or then look at this other KPI to see if that is also high, then there is some correlation we need to do, right? Or it could have other simple rules saying, never tell me about an access point down if the upstream switch is down or if the WAN link's down. Simple things, but it helps rely on things. We are, at this point in time, we have not finished one thing, which is to look at our telemetry and make decisions based on that. And that's what we are going to work on next year, saying if we know that a particular channel always has interference, then let's take it out of our channel plan. Make sure that we blacklist it for a certain period of time. Those kind of interesting things are things which we are now going to work on in 2020 by mining this very frequent information which we get out of the system. Couple of things I also wanted to mention as we started OpenConfig, right? Like one of the benefits which we had not thought about but kind of came about was earlier when we wanted to onboard a new vendor, it would take us months or quarters because we would have to rewrite our entire deployment and operations pipeline to work with the vendor. Now it takes us days to onboard a new vendor. And we were quite surprised that the sales teams for vendors actually like that, because now they are using this to their advantage, that, hey, we can get into your network sooner if we implement OpenConfig. As it stands right now, we have 2 vendors in production in our network using OpenConfig. There are 2 more who are in the lab. The hope is that by the time we come back in February, we have vendor number 3 in production, and vendor number 4 is working along in progress. So hopefully 2020 would be the year for that. OpenConfig does not mean that we are trying to go away from vendor proprietary things. We actually like the vendor proprietary things. We have various use cases where we need to use knobs. The message is simple. We want to use vendor proprietary knobs. We just need to be able to talk to you in a uniform way. So OpenConfig has capabilities in the models to include augmentation models for vendor proprietary things. So with that, we have about 9 minutes. So Mike, do you want to go in for the demo?
Yeah, let's give it a shot.
All right.
Let's see if it works. All right, so as Shimol mentioned, this is what we call a heat map. I don't know if you can really make it out, but it's just a floor plan with dots on it, and we enumerate phi layer information. So phi layer, typical things you do with a heat map: channel, transit power, channel width, and we do that per frequency. So on this example one, there's just one AP on there, and then the tool that he was referring to that we used to do the deployments, it's accessing a bunch of different APIs. So I just ran it. This is what you're seeing. It's accessing the Drive API to, interact with the interacting with the Slides API on Google Drive to get this sort of big JSON blob, so we can get the AP name and the channel and transit power and all that stuff. It's then interacting. So it generates this big JSON file, right, which is this. It's not really all that meaningful, but essentially this is the entire config. So that's how long it takes to generate the entire config, push it to the APs. It interacts with the revision control system, which in this case is GitHub. So it updates the GitHub file, and it's the same thing you were just seeing in that terminal. This just gives us an opportunity to track changes over time. So if somebody runs it and the channel would change, you would see the diff. Standard revision control stuff. So nothing too fancy there. What else did we want to point out? So the Drive API, the GitHub API.
Question on that.
Yeah.
Did part of your slide have the phi IP?
Yeah.
So it looked like it wrote one, but or did it?
So show the power and all those settings.
Sure.
On the phi.
We'll make that a little bit bigger.
On the heat
So, yeah, let me zoom in.
view. Maybe, I don't know.
That. So, as an example, we get the AP name. We title our sites by region. So U.S., NSH, Opryland. This was actually from last week or 2 weeks ago. The U.S. is the country, NSH is the site, and then Opryland would be the sort of the building. And then we just have increments. Like we start at AP01, which is the first floor, and -01 is the first AP, and we go up from there. So nothing too fancy there. Transit power of 9. 40 megahertz channel, channel 36. That's for 5 gig. And then transit power 4, 20 megahertz channel 11 for the 2.4 gig. And that's pretty much it. The nice thing about using any graphical system with an API for our heat map is that it has an XY coordinate system. So, X0, Y0 is at the top left. So we can do things like, as we're doing, after we do the post-install survey, the verification, we can say, well, I know that, in this example, you only see one AP, but imagine there was, 50 of them or whatever. You could do things like, I know 0101 is physically closer from an XY point of view to 0102. They're neighbors on the map. We call it like a map neighbor, a heat map neighbor. Now it's RF, so, everything depends on the walls and all that fancy stuff. But at the end of the day, if 01 is close to 02 physically, But then we look at the radio data, the RSSI, the neighbor table, and 0.1 is showing as closest to 0.9, which according to the heat map should be on the other side of the building. I mean, it doesn't matter whether there's walls or not, that's just a misplaced AP. So we can do things like automatically detect that the contractor has installed an AP in the wrong spot. I mean, we do other things, he was alluding to it, like we have a scanning app, so they just hit the barcode and then select, from the AP name, which is a list of APs that actually is generated from this same heat map. So we know the AP names, but they should be on the heat map. That tool uses the same APIs I do in the config generator to populate this list. So we try to sort of proactively help with associating the right AP name to the actual thing that got installed on the ceiling. As long as I've been in Wi-Fi, that's been a problem, getting the contractors to install it in the right spot. So, this helps us programmatically determine misplaced APs as well. What else? So in addition to pushing that, that config to the to GitHub, to the revision control system, right after it does that, it actually sends the config to the APs. So what you just saw, that's about as long as it takes to sort of configure the whole network, the whole building, all of the Wi-Fi. Did you say you had a question?
You want to show Viceroy?
Oh yeah, sure. Good one. So as just an example of revision control, we changed the channel. So then when it comes to monitoring, we do basically what most people do. You take a bunch of telemetry and you feed it into a database and you build graphs. Graphs are easy to look at, easy to digest data, and that we do the same thing. Like he was saying, this is our internal tool, but it's the same as Grafana or Prometheus or any of the open source ones that you may have heard of. In fact, in our deep dive class, that's what we do. We build this sort of end-to-end system using just open source stuff. And it looks very much the same. The background is black, not white, but other than that, it's just a visualization of data. So we see channel utilization there, and it's, per band. So this is the front end for our operations and NOC staff. This is what they look at. So it doesn't really matter whether it's an Aruba, Cisco, Juniper Mist, or Mojo Arista. They don't even need to know what AP is on the ceiling, because this is what they're looking at. They're just looking at 802.11, Wi-Fi data, and that's it. So we've abstracted that sort of vendor-specific foo from our operators, and that was the only way we could really do this at scale. Otherwise, we have to hire people that know the Cisco UI and people that know the Aruba, UI. So we don't have to do that anymore.
Is this for a single AP, or do you aggregate per floor, per building?
Everything is from the point of view of the AP. Now we have these things like selectors, so you can be like, okay, just do the start of the AP name -01.star, regex out, and it'll show you just the APs on the first floor. So yeah, you can show all of the APs in the building, and it'll overlay it onto one graph. Obviously, it starts to get untenable if you have 1,000 APs on one graph, just like anything else. But yeah, it is possible to sort of zoom out and in as needed, and then you've got your durations up here for timelines. We do this for client data, the radio data, pretty much all of the telemetry that we can get. Just want to reiterate, OpenConfig is built by us network engineers, not us Google. It's not a Google-owned thing. It's just network engineers that want to see this become a reality. So there's no association, there's no entrance fee, there's no copyrights, there's no lawyers. If you want to join, anybody can join. Reach out to, I'm here, reach out to me. We have our emails up on the screen in a bit. But, or openconfig.net is a thing. Don't complain to me about the look of the website. It's super basic, but that doesn't mean the project is not active. If you really want to see the activity going on, take a look at the GitHub repo. That's where all of the collaboration takes place, and that's where all the models are, including the Wi-Fi models. And we've got 24 seconds left.
Cool.
Just give it back?
Yeah, let's give it back 15 seconds.
All right. Thank you.
Thanks, everyone.